Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at Pure Math 3, Transcendental Functions Part 2, Logarithms and Exponentials, Modeling. So I'm excited about this because in modeling, you actually get to apply what you learn about logarithms and exponentials into a more realistic type situation. I actually wish Cambridge would develop this further. They don't regularly, this isn't a regular question type, but it does pop up once in a while, so you still need to know how to do it. Plus, it's really good practice at the mechanics that you learned in part 1. So let's get started, and first let me discuss the concept of how this modeling works. So let's say you're in your science lab and you're doing a biology experiment and you're recording data from your experiment, and you plot the data points with your two variables that you're using for your experiment. And so when you plot the x-axis versus the y-axis, your actual data seems to approximate some sort of a curve. Well, when it comes to curves, you might think it's pretty easy to identify. But if you don't get to see the whole curve, you don't know if it's a circle, an ellipse, a hyperbola, a parabola. You know, there are all sorts of different curves out there. And if you only are taking one segment of it, and if you take these different curves and you overlap them on one on top of the other, you can see that they're different, but it becomes difficult to know a circle from an ellipse, from a parabola, from some other curve when you only have a small segment of the graph to look at. So since you're in biology class and you're doing your experiment, you have this guess that your data is probably following either a power curve, like a quadratic or a cubic or some sort of exponent on your variable, or an exponential curve, but you might not be sure which one it is. So what you're going to do is you have your XY chart. This XY chart is what gives you your graph. So I didn't write the numbers in. This is, hypothetical here, but I did plot numbers on here. In my mind, I came up with my own problem for us. So here we have the point 1, 2. We could even write it in here. 1 gives us 2, 0. Let's start with 0. 0 gave us 1. 1 gave us 2. 2 gave us 4. 3 gave us 8. Now, probably already, you might have already figured out what I used, but remember, in a real experiment, these are probably going to be decimal values, or they're not going to line up exactly on the curve, but there'll be a curvish shape to it. And so you want to know, how can you model that curve? Why do you want to model it? Because the model allows you to predict future outcomes. It allows you to predict what will happen between the points. It will also allow you to predict what will happen if you extend further down the x-axis. So modeling becomes that's what math is about, modeling reality. So we want to figure out what that model is. So there are a couple of things that you can do. First, take the logarithm, actually the natural logarithm of the y value, and plot that against the x. So you go ln 1, ln 2, ln 4, ln 8, and plot that against 0, 1, 2, 3. And if that gives you a straight line, then that means you're going to have an exponential curve. If that still doesn't quite give you a straight line, then try taking the ln of both the x and the y values. So you'd have ln 0, ln 1, ln 2, ln 3, plotted against ln 1, ln 2, ln 4, and ln 8. If that gave you a straight line, then you would be dealing with a power function, such as a quadratic, cubic, something like that. Okay, so here we have, let's just walk through. What you're looking at is this straight line, and we know that a straight line follows the y equals mx plus c format. What we're going to do is we're going to use what we learned about logarithms and exponentials, and we're going to convert that into our model. And it can go either way. You can go from the model to this linear form, or you can go from the linear form to the model, and we'll look at both ways so that you can see how they work together. So let's start with the exponential here. So we have y equals mx plus c is the model for the line, but we replaced y with ln y. When we had y, it was a curve, and when we converted it to ln y, it made it a straight line. So we're going to trade our y for ln y, and this now is what models the blue line here. And so what you need to do is you need to calculate the slope of the line, which you should already know how to do that from junior high. Here, y2 minus y1 over x2 minus x1. Just pick 2 points, calculate the slope, and you find out the y-intercept, where it crosses the y-axis. So you're going to plug those values in for the m and for the c. Now, because we're just following along the math, I'm not putting numbers in, we're just going to follow the variables. So after you have your linear form where you've made your adjustments for your new chart here, then you're going to solve for y. We want to find that model with y as the subject that will represent the curve. So to get rid of ln, you have to exponentiate both sides, base e. So that means it lifts both sides up as the exponent. And remember your exponent rules. When do you add exponents? You add exponents when you multiply like bases. So this is a very important skill right here that will be helpful for you in some of the Cambridge questions, is to be able to take an e raised to an exponent that has an addition or a subtraction in it. And so addition means multiply, a subtraction would mean divide, of like base. So since base is e, then it's multiplied by e to the c. So this little step right here, going from that addition in the exponent level down to a multiplication on the normal script is crucial for you to understand. And it's just following your exponent rules. You're used to going this way. When you multiply like bases, you add exponents. We're just going the opposite way. Now, this e to the c, this is base e, or natural e, raised to a number, a constant, is still going to be a constant. So this e to the little c becomes a constant itself. So now it's represented by a capital C, because it's a constant. And it's multiplied by our e to the mx. And then if you want to simplify it a little further, your e raised to the slope is also a number. And that number, that e to the m, can be the base of your x. In other words, this is like an e to the m raised to the x. So the e to the m, because when you multiply, it's like an exponent raised to an exponent. We're kind of using your exponent rules backwards. So exponent raised to an exponent, you multiply. So you can take that x and raise it up there. That e to the m becomes the base. And that's what makes this an exponential function. And so this equation right here, this y equals big C e to the mx, now is the equation that represents your curve. You should be able to go back and plug in points and find out that this formula does represent your curve, and then you can use it for predictions of outcomes. Now let's work it the other way. And the reason why I want us to work it the other way is you really need to be able to go back and forth between logarithms and exponentials to really understand their relationship with one another. And it will help you in part one in that problem solving if you felt still not confident with that. This will really help solidify those skills. So if we want to go the other way, we're now going to ln both sides. Remember, you do the same thing to both sides of an equation. So we get ln y equals ln of c e to the mx. And remember your laws of logarithms. When you have a multiply, you can expand it into an addition. So ln y equals ln, and I put the e to the mx first, plus ln c. Well, the ln and e are opposites. They cancel, and so that drops the mx down to the normal script. So you get ln y equals mx plus ln capital C. So now hopefully you see the y equals mx plus c format. Your ln y is equivalent to the y. Remember, your ln y replaced the y here. Okay. Then you see your mx just like normal, and your y-intercept is ln of the capital C from here. So this right here is ln of that value is your y-intercept. So once you get it into this form here, you can easily figure out what your y-intercept is from this equation here. So you can go from your linear equation to your model or formula, or you can go from your formula to the linear model. Okay, so you're going back and forth between these two models using logarithms and exponents. The other thing that can happen is if you ln the x and the y. So you'd have ln y up here, and instead of just x, you would put the ln x here. So remember, you have to ln 0, 1, 2, 3, that would be the top, and you have to ln 1, 2, 4, 8, that would be the bottom. And when you plot those, if that is what gives you a straight line, then you're going to follow this over here. So you still have your y equals mx plus c, except now we replace y with ln y. We're replacing your y here with ln y here, and we're replacing x with ln x. Okay, so we replace x with ln x, we replace y with ln y. Then we e both sides to get rid of the ln. We exponentiate both sides, and the e and the ln cancel, giving us y. Now you might ask, why did we add ln if we're just going to take it away? Well, remember, the ln y is what we had to do to our data to make it a straight line. To get this y equals mx plus c, we had to do this logarithm application first. So it's actually starting out with ln y, but it's following a linear pattern. So we're really starting with ln y and then trying to make y the subject. So the e cancels the ln y, giving us y. When we exponentiate this side base e, again, remember that when you add in the exponents, it's because you multiplied like bases. So again, we're working backwards. And so we get this multiply here. And the e to the c again becomes capital C. But this time, notice up here, I think I forgot to mention the m, because this is a ln x. Over here it was just mx. But because this is a ln x, this m can become the exponent. That's your law of logarithm number 3, third law of logarithms that we covered in part 1. So this coefficient in the front can become the exponent of the argument. And so now the e and the ln cancels, and it drops this x to the m down to the normal script. The e to the c becomes the constant or the coefficient in the front, and now it's capital C. This is little c from your y-intercept of your line on the graph, and this is now capital C, a constant, which is the coefficient. Notice this now is your modeling equation that would represent your line if this is the situation that you have to make a straight line. And this is called a power curve because your x is on the normal script and it is raised to some exponent. Whereas over here, the x is in the exponent, and that's what makes it exponential. You have a numerical base, and x is your exponent, that's exponential. Here, x is your normal script base, and it is raised to some numeric power. So this is your power modeling, and this is your exponential modeling. But they're very similar. Your mechanics and your method are identical. It's just a matter of whether you're replacing one variable with ln or whether you're replacing both variables with ln. Now, if we work backwards, we ln both sides. So we get ln y equals ln c times x to the m. Again, we see this multiplication in the argument means we can expand and add them. So we get ln y equals ln x to the m plus ln c. And this, again, this exponent can multiply to the front. So ln y equals m ln x plus ln c. And again, we can see the relationship between this and our y equals mx plus c. So the ln y, replace the y. Here's your m for slope. Your ln x, replace the x. And again, ln c, ln capital C is your y-intercept. So they're very similar, but slightly different. Exponential and power. I noticed the Cambridge questions tend to focus on the exponential, but you should, the older book from Cambridge taught both. The newer one seems to focus more on exponential. Again, these questions do not occur that frequently, although I wish they would, simply because it is more application than simply manipulation of equations. But nonetheless, it is something that you need to be ready for, and it will really help you solidify your mechanics of how to do things. So let's look at the few examples that I could find from Cambridge past papers. Let me set up the first one. Okay, let's look at our first question here. Screen share. Here we have, you can see up here the code if you're interested in the past paper it came from. Two variable quantities, x and y, are believed to satisfy an equation of the form y equals c times a to the x. where C and A are constants. An experiment produced four pairs of values of X and Y. The table below gives the corresponding values of X and ln Y. By plotting ln Y against X for these four pairs of values and drawing a suitable straight line, estimate the values of C and A. Give your answers correct to two significant figures. It's worth 5 points, meaning you have about 7 minutes to do the question. Okay, let's go back to the board here. I kind of wish that Cambridge would start with the actual data set from the experiment. In Cambridge questions, they tend to throw you somewhere in the middle. They don't take you to the beginning X, Y values of some experiment. Like in this case, they said that there were four values of X and Y, and what they gave you was the chart of X ln Y. So in other words, they've already done some of that preliminary work for you, and they're kind of assuming that this is what will make the curve into a line. So we're kind of stepping into the question, not really at the beginning of it. And so remember, if this is what's going to make our straight line, here they're actually asking you to graph it. And in the Cambridge question, I didn't show you the part after it, but they do actually give you accurate graph paper, and you need to. If you try to do it by hand, freehand, you're not going to, you'll be close, but you're not going to get the exact accuracy that you need. So make sure that you're using accurate graph paper. This is actually the graph they provide. I just printed it out. And so you can see when I plotted their points, here's the 4 points. And so I plotted them here on the graph. And you can see that they don't exactly follow a line. So you have to do a line of best fit. So here's 1, 2, 3, 4 points. So I put in what I thought was a line of best fit. And notice that my y-intercept is exactly at 1.3. And I also calculated the slope. I used this point right here, which appears to be right on the line. And I also used the y-intercept, which appears to be quite accurate as well. So I used those 2 points to calculate the slope, and I ended up with my slope as 0.417. Okay, so here is my slope, 0.417. I get that from drawing my best fit line from these coordinates. Remember, use accurate graph paper. And then the y-intercept 1.3. So like I said before, you can either go from the line to your model. Here they've provided a general form of the model. You can also go from the model to the line. So let's start with going from the line to the model. So in this case, we're going to do y equals mx plus c, but our y is ln y equals our m is 0.417. See, here's our ln y. So ln y equals mx plus c, and our c is 1.3. This is according to my line. Yours might be slightly different. And so what the goal is to end up with the correct accuracy to two significant figures. So don't worry if your decimals are slightly different, although this one needs to be pretty close. This one is easier to get the right answer on. This one, that accurate graph paper will help you nail this one down. If you freehand it, you'll probably miss on it. So we want to e both sides. That canceled here, y equals, and so remember, plus means multiply, so 0.417x times e to the 1.3. Then this multiply can be raised as an exponent to an exponent. So y equals e to the 0.417x times, and now this e to the 1.3, so if we do e to the 1.3 on our calculator, we get 3.669 times 3.669, okay? And so we're going to make this the coefficient in the front, y equals, and I'm just going to change it now because we want two significant figures. I'm just going to put 3.7. And then in here, for the base, notice we have a base to our power. We're going to do e to the 0.417, and we get 1.517, and we'll just put 1.5 to the x power. So this e to the 0.417 is 1.5, and it's still raised to the x. So you can see that the big letter C is 3.7 and A is 1.5. Now, you could also get this going from the model to the linear. If you worked it from the model to the linear, you would ln both sides. Your ln then expands from a product of in the argument to an addition of logarithms. This is your expanding, this is your law of logarithms number 1 that we talked about in part 1. And then your law 3 takes this exponent and moves it to the front, which I rearranged it because ln A is actually now the coefficient. So this x moves to the front. It's now a product, so I just switched it around. So this ln A, now we're in our y equals mx plus c. You recognize that ln y has replaced the y value. So that means ln A is our slope. Okay, so you would get ln A equals, our slope was 0.417, which means A equals e to the 0.417, which equals 1.5. And your ln C is equal to the little c, the y-intercept. So ln big C equals 1.3. So then you would get big C equals e your big C, this one up here, the big C equals e to the 1.3, and big C equals 3.7. So you can get the right answer either way. You can work from the linear to the model, or you can work from the model to the linear. And the working back and forth really helps you to understand those relationships there. So that's our answer. 3.7, 1.5, and either way that you solve it, you get the same thing. And this is the first example. Let me set up for another one. Okay, let's look at our next example here. And here again, you see the code up here. The variables x and y satisfy the relation 3 raised to the y equals 4 raised to the 2 minus x. Part I, by taking logarithms, show that the graph of y against x is a straight line. State the exact value of the gradient of this line. Part II, calculate the exact x-coordinate of the point of intersection of this line with the line with the equation y equals 2x, simplifying your answer. Notice it says exact value of gradient and also exact x-coordinate, meaning we can't use decimals, so you have to keep everything in its exponential and logarithmic form. Okay, let's come back here to the board. Y to the x equals 4 raised to the 2 minus x. Now this particular question is still of the same type, although it's not really being applied to like experimental data. It just kind of throws you into this hypothetical situation. So this is what we're working with. It does say that by using logarithms, show that it makes a straight line, and then determine the exact value of the slope or the gradient. So we're going to take this and we're going to ln both sides. And this is y here. So remember your third law of logarithms, the exponents can multiply to the front. So this is y times ln 3. I'm going to put the ln 3 in the front because it's the coefficient of the y, equals, and we have 2 minus x times ln 4. So we want to distribute that ln 4, get ln 3y equals a negative, and again the ln 4 is going to be the coefficient of the x, so minus x ln 4 and plus 2 ln 4. So we distribute the ln 4 through the parentheses here. And then we want, because we're looking for slope, we want to get y by itself. So y equals a negative ln 4 over ln 3 x plus 2 ln 4 over ln 3. So we divide ln 3 through to make y the subject. So right here you can see the slope, y equals mx plus c. So our slope equals a negative ln 4 over ln 3. And there is our answer for the first part, the exact value of the gradient. Now, and we also show that this is y equals mx plus c. So this demonstrates that it does follow a linear pattern. Okay? Now we want to move on to the second part. So find the exact coordinate for x where there's an intersection between this line and the y equals 2x. So we're going to take our 2x here and set it equal if y equals this and y equals this, and they intersect, and that means this equals this. So we get a negative ln 4 over ln 3 x plus, and what I'm going to do is I'm going to bring this 2 up as the exponent, and so I'm going to put ln 16 over ln 3. So that way I can just write one number there, bring this number as the exponent, using that third law of logarithms. Okay, now our goal is to find x. So we have 2 x terms and a non-x term. So we want to put these together. So we get 2x plus ln 4 over ln 3x equals ln 16 over ln 3. And we want to factor out our x. 2 plus ln 4 over ln 3 equals ln 16 over ln 3. And it might be easier if we get a common denominator before we divide it. If we divide it the way it is, it's going to be a complex fraction with this addition in the denominator, and it's going to look kind of ugly. So let's get a common denominator first. So we want to multiply top and bottom by ln 3. So we get 2 ln 3 over ln 3, so multiply top and bottom here by ln 3, plus ln 4 over ln 3. And now it has a common denominator. This also can become the exponent. So that's ln 9 plus ln 4 over ln 3. And your condensing of an addition, your first law of logarithms, when you have the same logarithm, the addition means you can multiply the arguments. So this becomes ln of 36 over ln of 3. So this right here, if you work with it a little bit with your laws of logarithms, you can simplify it down to ln 36 over ln 3. So we're going to divide both sides by that ln 36 over ln 3, getting a little tight there. And so what we get coming up over here so that we have some room, x equals ln 16 over ln 3 divided by a fraction. So we're going to invert and multiply ln 3 over ln 36. Ln 3's cancel, giving us ln 16 over ln 36. Now, be careful here as you simplify. Remember, you cannot algebraically simplify from outside the logarithm to inside the logarithm. Meaning, I can't reduce this fraction. I can't go, okay, 8 over 18, or, divide both by 4 and you get 4 over 9 like that. You can't simplify that way like you can in algebra. So be careful to use laws of logarithms, not your algebraic simplification. What we can do, though, is we can change this to a ln 4 squared. You want to look for an exponent. Now, 4 squared over ln 6 squared. Okay? So that becomes 2 ln 4 over 2 ln 6, because those exponents can multiply to the front by your third law of logarithms. Now that they're outside the logarithm, now your algebraic simplification can take place. So the 2's cancel, and you get ln 4 over ln 6. This is our value of x. This is our exact answer. Now, you might say, what if I had put, instead of 4 squared, what if I had put ln 2 to the 4th, and over here got 4 ln 2, and then the 2 and the 4 cancel, and I get 2 ln 2 over ln 6. Is that okay? Well, it is okay. Technically, you do have the correct value. However, it's asking you to simplify it. And if you look at your law of logarithms, what you're looking at here is that third law. In other words, this 2 can come up as the exponent to make it 4. This is condensing. This is expanding. So Cambridge might allow it. They would probably allow that answer. But technically, if you want to simplify it, usually you want the condensed form, not the expanded form. So 2 ln 2 is the expanded part of that law, whereas ln 4 is the condensed part. So if you have a question, I would lean towards the condensed part of the law as opposed to the expanded part of the law. But they are the same thing, and if you got it down this far, Cambridge would probably allow that answer because you've simplified everything else. But here are exact values. Again, we started with just some equation that they threw us into. and they said to use logarithms to basically make it linear, and we did, and then we solved a simultaneous equation as well. Got one more question for us. We'll go back to the more practical type. I think that's what you're going to see more often, and it's also in the new 2020 test papers. So let me set that up really quick. Okay, let's look at our last example for this video. Here we have, notice this one is from the 2020, summer 2020, paper 32. So this is in the new syllabus cycle, and you can see that already they have asked a modeling type question. So it's another reason it's good for us to go over it. Again, they just jump right into this scenario where our xy from the original experiment is now x ln y. So they've already flattened out the curve into a line, and they provide us a modeling equation where we have to find out the components of that model. So the variables x and y satisfy the equation y squared equals a times e to the kx, where a and k are constants. The graph of ln y against x is a straight line passing through the points 1.5, 1.2, and 5.24 and 2.7. As shown in the diagram. Find the values of a and k correct to 2 decimal places. Again, it's 5 points, meaning we have 7 minutes approximately to solve this. So here is the graph that they have given to us, x graphed against ln y to get the straight line. To save us a little bit of time, because you already know how to find the equation of a line, I have already provided the slope. If you do y2 minus y1 over x2 minus x1, your slope is 0.4011. And the y-intercept, if you plug in one of those points into this equation, don't forget it's ln y, not y. So you got to make sure you do these values are ln y already. So if you plug in one of these for ln y and x, you get your y-intercept to be 0.5984. So this is our linear model for this straight line. What we want to find is the a and k of our model for the curve, which we didn't get to see what the curve was. Now, I said before that you can either work from the line to the model, or you can work backwards from the model to the line. And if you noticed in the first example that we looked at, even though I had done from the model to the line on the side, we actually worked from the line to the model. There is a situation here that you should be aware of. Normally, your model is y equals. In other words, y is the subject. In this model, y is not the subject yet. It is a y squared. So there's going to be a little bit of an issue here. You've learned order of operations with add, subtract, multiply, divide, radicals, and exponents. You know that exponents need to be done before adding or multiplying and dividing. You know that multiplying and dividing need to be done before adding and subtracting. You understand order of operations with the normal operations. But in this case, we're dealing with a square and a logarithm. So if you go from the line to the model, you're going to have to get rid of the logarithm, and you're going to have to add a square. And if you don't do that in the right order, you're going to get the wrong answer. Whereas if we start with this one, the square is already there, and you're going to find out that we don't actually square root both sides. when we introduce the logarithm, that's going to take care of itself. So this is my advice. If you're going to from a line to a model that y is already the subject, it really won't matter which way you go. But in this case, because the y squared, y is not the subject, I would recommend you go from the model to the line. It's easier because going this other way, again, you've got that square logarithm conflict, and we don't really have our order of operations to handle that with what you've learned. Okay, so we're going to go from the model and match the line. We know the line is correct. So let's make our model match this that we already know. So what we're going to do, we're going to line both sides. We're not going to square root. We're just going to line both sides first. Then, because we're using laws of logarithms, this 2 comes out as the front, the coefficient. So 2 ln y equals, whoops, I lined the left side. I did not line the right side. So ln a e to the kx. Notice over here, this is a multiplication, a product. So that means our law of logarithm, we add. So we have a ln of e to the kx. I put it first because it has the x term in it, plus ln of a. Now this ln to the e cancels, and so we have 2 ln y equals kx plus ln a. And now we can divide by 2. So we get ln y equals 1/2 kx plus 1/2 ln a. And what we want to do is we want to line that up over here so that we get ln y equals 1/2 kx plus 1/2 ln a. Now we can compare here. We see that the 0.4011 is 1/2 k, and we see that the 0.5984 is 1/2 ln a. So if we multiply this out, or we work with this, 1/2 k equals 0.4011. So all we have to do is multiply by 2. So k equals 0.80. And I think it only asked for 2 decimal places. And so we get 0.80 as our value for k. And then we want to take this part over here, 1/2 ln a is equal to 0.5984. So we get ln a equals, and when we multiply by 2, we get 1.1968. And then we e both sides, or exponentiate both sides. And so our a ends up being, when you do that on your calculator, your a ends up being 3.31. So again, the 2 decimal places with that. So again, be careful. You can go both ways, but in this case, if you went from the line to the model, you have that potential to get your exponent and logarithm out of order. So it's better to ln both sides, to work from the model to the line. In this particular case, you can try it and see that if you can get the model, but don't be surprised if you have some problems, but you can work with that. If you can work with that so that you can understand that relationship, that would be really good if you have time to do that. If not, I just recommend go from the model to the line. Here's your answers. And this is what modeling does, helps us to match math to an actual situation and then predict future outcomes. So thank you for joining me. Hope to see you next time for part 3, where we'll talk about sketching and derivative and integrals. And hope to see you again next time in the Zoom room.